Hi, good afternoon. Thanks to everyone for joining us. My name is Ariel Horowitz. I am the Grid Modernization Director at DOE's Grid Deployment Office, and we're very excited to have folks join us today for our interim webinar update on the Innovative Grid Deployment Pathways to Commercial Liftoff Report. We have a very full agenda for the next hour, but we're going to start off with a brief opening conversation with Maria Robinson, the Director of the Grid Deployment Office, and Vanessa Chan, the Director of the Office of Technology Transitions, on their perspective of innovative grid deployment before diving into early insights from the report with the full liftoff team. Let's get that conversation started. Vanessa, as the DOE's Chief Commercialization Officer, you've driven a lot of the pathways to commercial liftoff reports. What does commercial liftoff look like, in your opinion, within the grid landscape?
Great question. So we have a massive opportunity to unlock additional capacity and value from the existing T&D grid and to serve the load growth coming from economic development and support decarbonization priorities using an existing set of technologies. But these technologies have not reached at scale deployment. And so the thing I really want to stress that these technologies actually exist and we have to get them out in the marketplace. So we're entering into an extraordinary time where many parts of the country are seeing rapid load growth, generation additions, and resiliency threats all at once. And we need to build a grid that can handle these trends. And so many of the solutions are already sitting right in front of us. We need to get the commercially available, innovative technologies out the door on the existing system today. So while every commercial liftoff story is a little different, the story here is related to the LDES and VPP liftoff stories that we've already seen over the past year. But even more so than those stories, we don't need technology maturity or significant proof points or major cost downs here. We need to overcome key deployment barriers inherent in the market structure. So we're hearing from industry and regulators a growing interest in grid enhancing and innovative grid solutions, but we need to ramp the momentum. It will be a massive, massive miss if we don't work together to break these barriers down today. And so we need fast action to pursue a proactive investment strategy in available advanced grid technologies that are here right now that you can deploy today. And if we do it now, it is then the best for the long-term interests of Americans.
Hey, thank you, and thank you for that call to action. Maria, you stood at DOE's Grid Deployment Office. What is GDO focused on for grid innovation, and how are you addressing those priorities in the GDO funding programs?
Thanks, Ariel. So the Grid Deployment Office was found last year to help deploy federal funding for grid modernization as well as other grid technologies. And over the past year, we've committed over $7 billion in funding for tribes, states, local governments, and private industry in order to advance a more reliable, affordable, and resilient grid. And we actually have about $5 billion currently available across different programs and funding opportunities for the grid. So we're playing a really important role here at GDO as a catalyst to unlock opportunities for some of that private sector innovation and deployment. So we've designed specifically the Grid Resilience Innovation Partnerships Program, better known as GRIP, to support grid innovation and uplift those innovative partnerships between government and industry. You might have seen that we announced that first round of GRIP awards this past October, where we had about $3.5 billion in federal funding, and when combined with private sector commitments, about $8 billion total. And across those selections, that's going to support about 58 projects over 44 states. So we've opened the second round of that GRIP funding just last month, which is going to be similarly focused on helping to deploy advanced grid technologies and identifying some innovative approaches to improve grid resilience. We're really prioritizing in this round of funding projects that significantly increase transmission capacity, whether they're using advanced conductors or HVDC or grid enhancing technologies. We're prioritizing substation hardening projects, including automation or digitization of substations, as well as upgrades that support DERs and renewable integration. And in general, we're always supporting projects that are leveraging advanced transmission technologies, really trying to enhance the flexibility and reliability of the grid. And so you can check out more information on our website. We have a webinar about that particular opportunity as well in open FOA. But we're here today because we're really committed to working closely with our industry partners as well as the regulators to maximize the success and impact of federal funding for grid innovation and to ensure that these investments catalyze a long-term transformation of grid systems and technologies. And so we're really excited to have this liftoff report similarly focused on how to accelerate that deployment of innovative grid solutions.
Great. Thank you both for those perspectives. And now, without further ado, I will turn it over to Lucia Tian to dive into the interim report on the Liftoff project itself.
Thank you so much, Ariel, Maria, and Vanessa for starting this important discussion. And thank you all for joining us today. I'm Lucia Tian, Senior Advisor to the DOE's Chief Commercialization Officer and Acting Chief Strategist for the Loan Programs Office. For the rest of this session, my colleagues and I will walk you through an early peek into our upcoming innovative grid deployment liftoff work. Next slide, please. Before we begin, please note that DOE is only communicating public and non-privileged information during this webinar, and we will not be discussing the details of any specific program opportunity, for example, requests for information, notices of intent, or funding opportunity announcements. Questions about specific DOE programs and funding opportunities should go to the relevant DOE office. This webinar is part of the broader DOE Pathways to Commercial Liftoff initiative. Earlier this year, we published reports covering the commercialization landscape for clean hydrogen, long-duration energy storage, advanced nuclear, carbon management, industrial decarbonization, and virtual power plants. The Liftoff reports represent a department-wide initiative to strengthen engagement between the public and private sectors to accelerate the commercialization and deployment of key clean energy technologies. We aim to provide a common fact base for public and private sector investments and decision-making in that shared pursuit. We're currently developing a similar perspective on the deployment of innovative and commercially available grid technologies, the topic of today's webinar. As context for the rest of this webinar, this liftoff work is focused specifically on accelerating deployment of commercially available technologies on the existing grid. Other important grid modernization efforts, such as pre-commercial R&D topics and permitting for new builds, are not part of this work, but covered elsewhere. We very much look forward to your input and engagement on this important topic as we continue to develop our perspective. Please send all questions and comments on this presentation to liftoff@hq.doe.gov. Key topics we'll cover today include the operating context that we see impacting grid investments, an overview of our liftoff report scope, highlights of 4 priority technologies for deployment, and emerging insights across the broader suite of deployable grid technologies. If you need to step away early, a recording will be available at liftoff.energy.gov. With that, let's begin with a few key messages. Given the pressures our electric grid is facing, stakeholders across the board are emphasizing the need to shift to a proactive, future-oriented approach for managing and investing in the grid to ensure system reliability in a rapidly changing energy system. Both industry and regulators recognize that current regulatory and business models make it challenging to invest in advanced, innovative grid solutions that go beyond the maintenance of existing infrastructure and development of traditional assets. And the status quo here isn't an option. Communities and utilities that fail to invest in and modernize the grid in the near term will struggle to provide reliable and affordable power over the coming years, putting at risk human well-being and economic development opportunities. Rapid load growth in many parts of the country is impacting utilities' ability to meet demands today. In these areas, there's urgency to expand system capacity and invest in some of the readily deployable grid solutions we'll tackle in today's webinar. Manufacturers are also telling us that grid reliability is increasingly a competitive differentiator for where they will build new plants and create new jobs. And there's an essential equity dimension here. Disadvantaged communities are already vulnerable to outages and face the most significant risks of an unreliable grid. Inaction is not an option for these communities. Given the pace at which these pressures are impacting the grid and the need to keep rates manageable amidst a huge need for grid investment, the industry will increasingly need to get more out of the existing grid infrastructure to be able to deliver reliable and affordable power. Fortunately, we do see a lot of opportunity before us. The existing transmission and distribution grid is a powerful resource that can be enhanced through multiple readily available innovative technologies and applications that can be quickly scaled today. This suite of innovative grid solutions includes a range of system automation, grid enhancing, and capacity expanding technologies. Deployed strategically, they can significantly expand system capacity while building the foundation of a modern grid that is more dynamic and flexible to meet emerging needs like renewable integration and transport electrification. These innovative grid solutions are technically proven and commercially available, yet deployment and associated industry know-how is lagging behind. Technology maturity is generally not the challenge here, as it can be for several other clean energy technologies we've explored in the Liftoff series. Rather, market and regulatory structures need development to sufficiently incentivize innovative grid deployments and overcome industry-wide challenges to new technology adoption. Accelerating deployment also requires building industry know-how, including developing technical standards and certification processes, improving evaluation methods to holistically value and monetize benefits and costs, and building internal capabilities to integrate those technologies into core investment and operational processes. In the full Liftoff report, we'll look into the broad suite of technologies, but today we are focused on 4 of the technologies that are high priority for rapid scaling: dynamic line rating, or DLR, advanced conductors, high voltage direct current lines, or HVDC, and advanced distribution management systems, or ADMS, and its advanced applications. These 4 are in focus for us because we believe these solutions can have significant impacts on rapidly expanding grid capacity in the near term and building the foundation for a more reliable and resilient grid in the long term. But we're seeing a mismatch between the high system value these solutions can bring and the level of industry interest in these technologies within our DOE programs. DOE funding programs, including GDO's GRIP program that Maria mentioned, are available to accelerate more early deployments and catalyze broader uptake of these types of innovative solutions. Utilities, regulators, policymakers, solution providers, and other key stakeholders can start acting today, taking advantage of unprecedented federal investment and policy incentives to accelerate deployment of innovative solutions that can unlock meaningful near-term value. And I want to get more specific here on opportunities we see for stakeholders to pursue today to support investments. To continue providing reliable, safe, and affordable power, grid operators can start evaluating innovative grid solutions in existing investment processes to identify and deploy no-regrets bundles. And they can start developing a holistic, long-term oriented grid modernization strategy to identify further opportunities. To best serve their ratepayers, regulators can ask for or require innovative grid solutions to be considered in existing utility plans and proposals. Just asking for these solutions to be considered can surface easily overlooked high-value opportunities. Concurrently, regulators can begin exploring solutions to align regulatory and business models with the needs of a modern grid. Policymakers, through legislative actions or state energy offices, can coordinate with state regulators on these efforts to protect constituents and further economic development priorities. Finally, solutions providers can be more proactive in articulating, quantifying, and valuing the benefits of their solutions to support utility investments, contributing to industry standard setting and education, and even sharing in performance risk for proven but subscale technologies. Across all of these stakeholders, there's an opportunity to leverage available federal funding to begin future-proofing the grid today by accelerating innovative deployments. While there are many broad challenges to overcome, our early findings from this liftoff effort are clear. We can start acting today to deploy more of these important grid technologies to address pressing capacity and reliability needs. Now I'll hand it over to my colleague, Avi Gopstein from the Grid Deployment Office to share an overview of the grid context and the needs we're seeing.
Thanks very much, Lucia. So one thing I'd like to emphasize is that innovative technologies does not mean pre-commercial technologies. Across the country, utilities are already investing in and benefiting from the innovative grid technologies that we're discussing today, as well as many other grid modernization solutions. And here you can see just a few of the utilities that have already built projects that are operating their systems utilizing these technologies. But there are more than 3,000 utilities in the United States, and a few excellent projects won't get us where we need to be. An aging energy system and evolving system dynamics and rapidly diversifying and expanding generation capacity means investment in grid infrastructure and innovative technologies must accelerate to address emerging system pressures. Over the next 10 years, our grid will continue to age and assets will need to be replaced. And at the same time, we expect to see significant increases in load, a changing supply landscape of DERs and greater renewables penetration, and increasing weather and other shocks to the system. This is driving a significant need for greater system flexibility driven by enhanced T&D capacity and more modern, sophisticated grid management capabilities. However, investing in innovative solutions can be challenging. Through extensive conversations with industry over the last several months, we're hearing about the competing priorities of maintaining an aging system while planning for future system upgrades, as well as the need for efficient capital allocation to minimize ratepayer impacts. We're hearing about the need for new processes to better evaluate emerging technology benefits when technology is first deployed, and for a future when it is utilized at scale. And we're hearing about the constraints regulatory and business models place on utilities' ability to adopt new technologies. From these conversations, it's clear that legacy approaches to capital allocation, which often depend on a maintenance framework built on a foundational assumption that existing infrastructure is sufficient to serve load, are no longer adequate. Aging infrastructure, growing and increasingly variable load, evolving reliability strategies and requirements, and modern information systems each impact the grid in unique ways. And so proactive planning and investment strategies that modernize an organization's approach to meeting grid demands are needed. These may include longer-term horizons for capital allocation, leveraging complementary infrastructure investments to improve capital efficiency and minimize aggregate ratepayer impacts, and aligning business and regulatory models with emerging customer expectations, benefit streams, and technologies. We are hearing from industry that we have to shift from a business-as-usual approach for infrastructure development to proactive, forward-looking investment strategies. And I'll hand it over to my colleague Isabel to take us through how this liftoff report fits within the broader set of DOE efforts supporting transformative grid investments.
Thank you, Avi. Hi, everyone. I'm Isabel Sepulveda. I'm a project manager with the Grid Deployment Office. So as Avi was mentioning, recognizing the significant investment needed for modernizing the grid, DOE has a variety of funding programs and initiatives available in this area. Importantly, these efforts are intended to support greater partnership with industry, because we recognize that only industry can drive and execute the massive changes we're discussing, while our role is to serve as a catalyst for greater market adoption. These funding mechanisms are complemented by several ongoing DOE initiatives across a range of topics. As you can see in the bottom left-hand corner, the liftoff report we're discussing today is one of these initiatives and is intended to be DOE's fact base to guide our partnership with industry. Before diving into the liftoff report, I want to highlight one open funding program that is particularly relevant for the liftoff scope. As Maria Robinson mentioned in her opening remarks, GDO's Grid Resilience and Innovation Partnership Program, or GRIP, is a $10.5 billion funding program focused on 3 topic areas: grid resilience, smart grid, and grid innovation. This program is currently open for applications with a deadline for concept papers coming up soon on January 12th. While it is a substantial amount of funding, GRIP cannot cover the full cost of maintaining or replacing existing infrastructure across the US. So this program is really focused on where DOE funding can be a catalyst for broader deployment of innovative grid solutions. So without further ado, let's get to the liftoff report. The focus of this forthcoming report is to identify pathways to accelerate the near-term deployment of innovative, commercially available grid technologies and applications on the existing T&D system to expand T&D capacity and build critical modern grid capabilities. One note on the technologies and scope. Due to the success of past R&D efforts, there is a cohort of technologies that are now ready for commercial scale-up, which is where this liftoff report is focused. We are not covering pre-commercial technologies, which is the focus of other ongoing R&D efforts within DOE. With that, I'll turn it over to Louise White from DOE's Loan Programs Office, who will walk us through the technologies in focus.
Thanks, Isabel. So for our liftoff report, we've identified around 20 innovative grid technologies and applications based on their commercial readiness to expand and build a modern grid. These technologies fall across 4 strategic priorities. 1, retrofitting the physical system with advanced transmission technologies to rapidly expand capacity. 2, building situational awareness and system automation to improve visibility, system efficiency, and decision-making. 3, deploying grid enhancing solutions to better optimize and adaptively control a more dynamic grid. And 4, deploying the foundational data systems needed to enable these other innovative technologies. Of these 20, we're going to dive further into 4 of these solutions today: advanced conductors, HVDC lines, dynamic line rating, and ADMS and the advanced applications it unlocks, like VVO, DERMS, and FLISR. These 4 are in focus because we are finding the solutions can have a particularly large impact on rapidly expanding T&D capacity in the near term while building the foundation for a more reliable and resilient grid. Yet we are hearing from industry about the implementation hurdles that are slowing investments in these types of technologies. And we recognize an opportunity for federal funding to play a role in overcoming some of these hurdles to help catalyze widespread adoption. So where do we see a role for federal funding in overcoming some of those commercialization challenges? For DLR, public funding can lower upfront costs to mitigate mismatched incentive challenges and support programs to standardize performance testing and certification processes. For advanced conductors, public funding can reduce the higher upfront costs to support project economics, which can be harder to justify in current least cost investment processes. For HVDC systems, public funding can reduce the cost of HVDC projects to stimulate the demand needed to support domestic supply chain development. And funding is also available to support that supply chain build out. For ADMS and its advanced applications, public support can de-risk these investments, removing some of the benefit and cost uncertainties to help lay the foundation for a modern distribution grid. These 4 technologies are the types of innovative grid solutions that DOE programs, such as the GRIP program, are well positioned to support today to catalyze investment while longer-term solutions are pursued. So we'll briefly dive further into each of these technologies to better understand their value prop, barriers, and why we see a need for greater deployment in the near term. So starting it off, I'll hand it to Ishan to get started with DLR.
Thanks, Louise. Dynamic line rating, or DLR, is a grid enhancing technology that improves the utilization of the existing transmission and distribution system to increase effective capacity. DLR sensors assess current environmental and line conditions to set line ratings based on how much current can be safely carried through lines in real time. This is an improvement over traditional static line ratings, which are based on conservative assumptions rather than real-time conditions. Think of static line ratings like setting a highway speed limit based on the most treacherous winter conditions, whereas DLR sets a safe speed limit based on weather conditions in the moment. Based on these features, DLR has a strong value proposition. It can increase effective transmission and distribution capacity on existing rights of way by giving a more accurate view of a line's true carrying capacity. Based on past deployments, DLR can increase effective capacity by an average of 10 to 30% over 90% of the time. The expanded capacity can relieve congestion, reduce curtailment, and improve interconnection outcomes, particularly in capacity-constrained or highly congested areas. Additionally, DLR is significantly more cost-effective and easier to implement when compared with new builds. It can also improve system reliability, efficiency, and planning. Despite these benefits, US DLR deployments are limited, largely due to the misaligned incentives with traditional CapEx-driven utility business models and DLR costs accruing to utilities while benefits accrue to ratepayers. Other key barriers include a lack of broad awareness of and clarity on DLR benefits, particularly around performance reliability, quality, and implementation processes, a need to modify operational practices to integrate DLR, and a need for greater industry testing and certification standards. But these barriers can be overcome, and deploying DLR is often worth the effort to quickly increase effective capacity. DLR has been tested and deployed in the US and widely in Europe, with many case studies proving out its maturity and benefits. In New York, National Grid took a strategic approach to address wind curtailment challenges by looking at where DLR made the most sense to complement other capacity expansion plans, bringing down overall costs and successfully reducing curtailment. Encore piloted DLR in Texas to address congestion challenges. The solution increased effective capacity by 5 to 10% and nearly eliminated congestion. Pennsylvania Power and Light recently invested $300,000 in 2 DLR deployments, which are expected to drive $23 million in annual congestion cost savings, which directly benefits their ratepayers. DLR is a proven technology that can quickly unlock additional effective transmission capacity. This will help tackle the challenge of rapidly rising congestion costs in the US, which is estimated to have more than tripled in the last 2 years and is expected to keep rising. This negatively impacts ratepayers who bear the brunt of these costs. DLR is an available and proven, yet underutilized solution. It can rapidly increase effective transmission and distribution capacity, which can reduce congestion, lower energy bills, and support near-term economic priorities. Federal funding, like GRIP, is available and intended to accelerate deployments of innovative solutions like DLR. Now I'll hand it over to Isabella to cover advanced conductors.
Thanks, Ishan. Advanced conductors are another class of technologies that can increase capacity and improve power line performance on existing rights of way. We define advanced conductors as designs that can double line capacity with limited sag and that significantly improve energy efficiency versus conventional ACSR conductors and ACSS conductors. These advanced conductors typically consist of a composite-based core that can support more conductive aluminum for the same weight. There are several key benefits to using these advanced composite core conductors. First, they can cost-effectively and quickly double transmission capacity on existing rights-of-way. Second, their low electrical resistivity reduces line losses and translates to energy savings to ratepayers. Third, composite cores have very high strength and relatively light weight. This can reduce line sag and enable safe and reliable operations at high temperatures and in extreme weather. However, there are several barriers to increasing deployment of advanced conductors. One big challenge is that the upfront costs are around 2 to 4 times higher than conventional conductors. And this limits the competitiveness of advanced conductors in the least cost investment models typically used by state regulators to approve transmission plans. Utility investment models also tend to undervalue efficiency gains, which is an area where advanced conductors could provide substantial benefit to customers. These two barriers contribute to the perception that advanced conductors are uneconomic today, despite the significant capacity, efficiency, reliability, and resilience value they bring. Scale-up is also slowed by implementation challenges, like needing to train technical crews on new installation methods
and needing greater technical standardization of advanced conductors and their accessory parts. Despite these obstacles, advanced conductors offer multiple advantages over conventional conductors. This is especially true for utilities and localities facing challenges such as load growth, long interconnection queues for new energy sources, congestion, rising ratepayer costs, or more frequent and severe weather. These utilities should consider advanced conductors, especially when reconductoring or replacing aging infrastructure, because they can double capacity while improving efficiency and reliability. Advanced conductors reduce power line losses by 20 to 40% compared to ACSR and ACSS conductors, which can lower ratepayer costs and reduce the need for peaking generation. Their characteristic low sag and ability to operate safely in extreme environments significantly improves reliability as well. And all of this can be implemented on a much quicker timeline than new build projects. Already, we've seen the benefits of advanced conductors in domestic and international projects. For example, American Electric Power used advanced conductors to address load variability challenges in Texas. The project was approved in ERCOT in one day and nearly doubled line capacity without requiring any widening of the right-of-way. The advanced conductors improved line efficiency by 30%, which has saved AEP's customers millions of dollars annually. In California, SoCal Edison used advanced conductors to increase transmission capacity. Because of their low sag, SoCal Edison could do this on existing structures without violating sag clearance limits. Looking even more broadly, we've seen advanced conductors being implemented around the world for over a decade. With hundreds of projects already in action globally, the technology is mature and it's ready for scale up in the US. However, in the US, project valuation processes do not fully capture the benefits of advanced conductors, and this creates a major challenge to their deployment. As you can see on the figure to the left, reconductoring with advanced conductors can cost around twice as much as with conventional conductors. However, advanced reconductoring is only about half the cost of new build projects that may otherwise be needed to expand capacity. Current least cost planning processes focus on this upfront cost, where conventional conductors win out compared to advanced options. However, as we've discussed, advanced conductors offer significant value in increasing capacity, reliability, and energy efficiency on a quicker timeline versus alternatives. This full suite of benefits is not usually considered in decision-making, and even when some benefits are, such as energy efficiency savings, when models use a high discount rate, they can undervalue the lifetime efficiency benefits of advanced conductors for ratepayers. Under the current valuation process for transmission planning, advanced conductors can appear uneconomic. However, they can address near-term capacity needs and improve performance, and therefore should be considered in reconductoring and rebuild projects. Updating grid planning and valuation methods can enable more holistic investment decisions to support advanced conductor deployment at scale. But in the immediate term, federal funding, including the GRIP program, is available to reduce upfront costs and support the project economics of advanced conductors today. I'll now hand it back over to Ishan to cover HVDC.
Thanks, Isabella. The third technology we'll cover is high voltage direct current, or HVDC. HVDC systems are powerful tools that can increase transmission capacity while also providing significant reliability and resilience support to the existing grid. HVDC systems include two components: DC transmission lines and converter stations. HVDC systems are primarily valued for their increased transmission capacity over long distances underground and underwater with low energy losses versus HVAC, or high voltage alternating current. In addition, HVDC's greater controllability and flexibility bring significant benefits to the greater grid, including market optimization, reliability, and resilience benefits at lower costs than their alternatives to achieve these same goals. Key barriers impacting HVDC deployment include bottleneck supply chains, a need for greater technical standardization, extensive multi-stakeholder collaboration to plan projects and really ensure that broader buy-in that's needed for project success, and revisions to current investment processes to holistically value HVDC's system benefits. These barriers exist on top of typical new build challenges, including permitting, price, and planning. Bottlenecked global supply chains are considered the largest barrier to new projects today. Building a domestic HVDC supply chain is an opportunity for the US to accelerate HVDC commercialization. Let's dive into what can really make this happen. Without addressing supply chain challenges, US HVDC projects will continue to struggle. Stimulating domestic demand is an opportunity to incentivize US-based supply chain development. Currently, global supply chains are struggling to meet HVDC demand. The chart on the left shows demand has tripled in the last decade, creating lead times of over 7 years for critical HVDC components. The US has an opportunity to overcome this supply chain challenge and build greater domestic capacity. The three main HVDC converter suppliers globally, GE, ABB Hitachi, and Siemens, have limited US manufacturing despite having a robust US presence in other areas. A lack of domestic manufacturing creates a dependence on stretched foreign markets, which increases the risk of failed projects and creates further uncertainty for prospective developers. A strong and secure demand signal today is required to incentivize these types of manufacturers to build capacity in the US and protect industry's access to HVDC supplies long term. There is an opportunity to leverage DOE infrastructure funding, such as GRIP, LPO, Title 17, and the Transmission Facilitation Program, as well as advanced manufacturing funding, such as the 48C tax credit, to both stimulate demand and build domestic supply chains. There are a variety of cost-effective HVDC use cases that can build demand and support domestic manufacturing. They vary in complexity and market size, but all of them leverage HVDC's unique benefits to solve near and long-term challenges on the grid. The first use case for HVDC systems is high-capacity infeeds to large load centers, which is increasingly important as city densification drives up transmission capacity, but right-of-ways remain constrained. Number two is upgrading existing rights-of-way via converting HVAC corridors to HVDC and replacing HVDC lines that are aging. This can quickly double or triple transmission capacity to maximize existing rights-of-way while adding reliability and resilience support to the grid. Third, HVDC systems can cost-effectively connect offshore wind projects via submarine cables with limited energy losses. There's already some domestic supply chain for subsea cables in South Carolina, but it needs to be expanded to meet offshore needs. The fourth use case is the interconnection of asynchronous grids and balancing areas, which greatly improves renewable integration and general grid reliability. HVDC systems are often the only technically feasible solution to accomplish this. Last but not least, long-distance bulk transmission is needed to transfer lowest-cost clean energy generation to consumers. HVDC's grid reliability and stability support is especially valuable when connecting to weak AC grids. We expect the market opportunity and economics to become even more attractive when considering the full range of grid reliability and resilience benefits that HVDC can bring to the system. So developing holistic benefits assessments is an ongoing priority to further support HVDC projects. All in all, HVDC systems can transform our grid by increasing reliability and resilience while directing cheap and clean energy to consumers. Public funding can help stimulate demand to build a stronger domestic supply chain and secure our access to HVDC systems. Now handing it over to Angelina to cover advanced distribution management systems.
Thanks, Ishan. The final technology we're going to discuss today is Advanced Distribution Management Systems, referred to as ADMS. ADMS increases visibility and situational awareness on the system and automates processes that exist manually today. Additionally, ADMS can unlock other adaptive control technologies, such as volt var optimization to increase energy efficiency, fault location, isolation, and service restoration devices, which increase resilience and reliability, and distributed energy resource management system, which enables better visibility and control of DERs. Transitioning to an ADMS can improve data quality and data processing speeds for increased overall operational efficiency. Additionally, better system visibility can help identify problems on the system faster, which can often lead to faster restoration times. Finally, this increased situational awareness also increases data granularity that can better inform future grid maintenance and investment decisions, such as taking a condition-based maintenance approach to distribution assets. However, there are several challenges to successful implementation of ADMS. First, implementing a new operational technology on the distribution system requires extensive change management within the organization. Second, implementing an organization-wide integrated management system is technologically complex. It requires managing the migration of old workflows and databases into a new system, a large number of devices that must work together, and you need to trust in the accuracy of the data in the automated environment. Finally, making the case for ADMS investment can be challenging, as benefits may not be realized for many years and often only look at the benefits of individual ADMS advanced applications. Despite barriers to implementation, there are numerous instances of successful ADMS projects, with a few showcased here. First, Arizona Public Service activated their ADMS in 2017 after realizing a need for more advanced DMS capabilities to manage increased DER penetration and time of use rates. APS increased situational awareness, which allowed them to increase operational efficiency, pinpoint load and generation on their system, and improve system reliability. APS specifically was able to leverage their new ADMS system to de-energize power lines remotely during a recent wildfire event and return power quickly once it was safe. Second, Unitel implemented ADMS to improve storm management and DER integration capabilities. This ADMS improved outage response times, lowered system peak load, and overall reduced costs to ratepayers, with additional future benefits expected from VVO and DERMS. Lastly, First Energy leveraged ADMS to combine 10 disparate legacy systems. Their ADMS flexibility to layer on existing systems proved highly valuable to improve situational awareness and outage restoration times, and also reducing operational costs. There are significant benefits that could be unlocked from an ADMS, but it can be difficult to successfully deploy ADMS. For example, it can be very expensive. The graphic on the left shows results from 50 interviews of investor-owned utilities conducted by Wood Mackenzie, published last month. 30 out of 50 of these IOUs interviewed are actively investing in ADMS, showing that utilities are seeing the benefits of this investment. However, the total cost of these programs is roughly $1.3 billion, which translates to an average of $43 million per utility. So that ADMS is a large undertaking for a utility. Federal funding is available to de-risk early investments in ADMS and buy down these initial upfront costs. Additionally, following best practices where deployment can support success. First, using a targeted incremental strategy can help avoid cost overruns and timeline slips and allow for a modular approach, which in turn can allow the utility to identify quick wins for customers and regulators. Second, when conducting the benefit cost analysis for these studies, ensure all benefits are captured and consider a longer time frame for the return on investment. Finally, ADMS can build upon existing operating technologies rather than require a total system overhaul. Now I'll hand it back over to Louise to summarize.
Awesome. Thanks, Angelina. All right, so we just did a deep dive on 4 priority technologies that we see as bringing a lot of value to the grid in the near term. But that's not all. In the full Liftoff report, we are looking at that broader suite of commercially available, innovative grid solutions that we highlighted before. So we'll wrap up today by sharing a few early insights on this broader suite of technologies, starting with their readiness to scale. So while all of these grid solutions that we're looking at are technically proven and commercially available, they do vary in terms of their deployment readiness. We find that these technologies fall across 3 deployment stage categories. The first is scale commercial deployments, which includes technologies where market adoption is limited and below where we might expect given the high technical maturity of these solutions. This category includes the 4 technologies previously highlighted. The second category is early commercial deployments, which includes technologies that have more recently reached a higher technical maturity and are now poised for early scaling. The third category is large-scale operational demonstrations, which includes solutions that are a little earlier stage and need that large commercial demonstration to better understand operational performance and integration before broader scaling. Now, when looking at these, the question comes up of what is holding deployment back, particularly for those mature technologies that are ready for scale deployment. In addition to a few specific technology barriers, we are hearing that this is largely due to a lack of sufficient investment incentives to warrant the significant organizational effort required to deploy many of these innovative solutions. This again highlights the need to shift from traditional cost of service models that often disincentivize these types of innovative investments and towards business models that appropriately reward utilities for these types of investments that are needed for a modern grid. Now, despite these challenges, when looking at the outcomes that these solutions lead to, we see that investing in overcoming these challenges is often well worth the effort. So let's take a look at those outcomes now. When we evaluate the impact of these solutions on the grid, we see that each contributes in multiple ways to enhancing grid capacity to make the most of existing rights of way today, and toward achieving modern grid objectives by improving the system's affordability, environmental sustainability, reliability, resilience, safety, and security. Here we have scored each technology based on the value it brings towards these grid outcomes. In the full liftoff report, we'll cover each technology and application in more depth, but we won't get into too much detail there today. But looking at each technology individually only tells part of the story. Understanding and capturing the full value of these types of innovative grid solutions requires viewing them as part of broader interconnected systems. So let's walk through a few high-level examples to see what this systems part really means. On this page, we have our 4 categories of technologies that we've been discussing: the foundational, situational awareness, grid enhancing, and advanced transmission solutions. And then on the right-hand side, we have those target grid objectives that we just spoke about: T&D capacity, improved reliability, and so on. And while this isn't a comprehensive list of grid technologies or systems by any means, to be strategic with our capital investments, we really want to understand how the technologies in scope are part of larger interacting systems that affect potential outcomes and benefits. So let's look at a specific example, an advanced dynamic line rating application. As we've discussed, DLR drives multiple capacity, reliability, decarbonization, and affordability outcomes. But to implement advanced DLR technology requires installing sensors to measure real-time environmental and line conditions, which also significantly increase system visibility. And since in this case, we're looking at an advanced level of DLR, automating and digitizing substations will enhance line voltage and current control, amplifying DLR's benefits. But sensors alone don't accomplish anything. And so DLR also requires foundational communication and data management systems to transmit and handle the increased data coming into the operations center and to implement the line rating change on the system. So effectively deploying DLR requires deploying a number of other systems if they're not already installed. And DLR is not the only technology for which this is the case. So this holds true for other solutions. Shown here is topology optimization, which efficiently routes power flows to maximize the use of existing wires and improve reliability. Reconfiguring grid topology requires a range of physical and back-end supporting systems, examples of which are highlighted here in the first 2 columns. And the combinations of systems and benefits can become more or less complicated, depending on the application and level of innovation you're seeking. For example, advanced power flow control in the distribution system can yield many benefits, but for the most innovative approaches and applications of advanced power flow control, it requires deploying several supporting systems and technologies, like ADMS and others. But fortunately, not every technology is as complicated. Advanced conductors, for example, can yield a significant number of benefits without requiring updates to other operational or back-end systems. So let's take a look at these systems all together. And it's when taking this integrated view that 2 important things stand out that I want to highlight. First, the benefits that flow from these technology investments are complementary and can stack. For example, each of the 4 highlighted solutions enhance transmission and distribution capacity, but they all do it slightly differently. And so the net capacity benefits realized across the set of interacting technologies can be far more impactful than could be achieved through any one technology deployment. Second, because common systems like communications, data management, ADMS, and others undergird many advanced grid solutions, being strategic about investment in these infrastructures can prepare a utility to unlock additional benefits down the road and improve cost sharing between technologies. But to capture that future value, System investments today must be strategically planned to meet needs in ways that open future technology pathways to modernization. For example, investing in high quality of service communications can support an ADMS system today, but then also enable grid protection schemes and advanced power flow controls in the future. Now, this doesn't mean that every utility needs to have best-in-class foundational systems by any means. Innovation comes in many flavors, and considerable benefits can be realized with more basic technology investments. So a strategic investment plan must identify the appropriate level of innovation and supporting technical requirements to best support a diverse array of potential future applications to meet a utility's current and future grid needs. This requires that utilities consider how to evolve operational strategies to enable these new grid solutions, what level of innovation is most appropriate for their own needs, and how to best capture the complementary value of these systems, including shared technical requirements. Due to the complexity of these systems, a forward-looking strategy is necessary to right-size infrastructure investments for maximum return. Without such an approach, there is a real risk of wasting precious capital resources on duplicative or ineffectively scoped foundational systems. But when done well, these considerations for strategic investments can allow utilities and customers to realize immediate benefits from technology and subsystem deployments today, while simultaneously pre-positioning the utility and lessening the costs to realize new and compounding benefits in the future. The ultimate takeaway here is that understanding and valuing innovative grid solutions like the ones we're looking at within this liftoff effort requires looking at the system holistically to recognize complementary and stacking benefits and to strategically plan for the long term to ensure capital is deployed efficiently today. Now, as we start to wrap up, I want to highlight some of the cross-cutting barriers and solutions that need to be addressed to support greater deployment of this diverse set of grid solutions. We are finding 5 key cross-cutting themes that need to be addressed. First, developing and adopting standardized planning and investment methods that are long-term oriented and holistic can address the current lack of set methodologies to understand and evaluate the benefits and costs of these types of innovative solutions. Second, updating regulatory and utility business models can address the meaningful misalignment between traditional incentive structures and the needs of a modern grid. In particular, structures that reward and value performance instead of capital expenditure, enable new risk and cost sharing models, and encourage innovation can drive commercial liftoff for these solutions. Third, proactive, future-oriented investments in organizational capabilities and operational processes can help address the implementation complexities that slow the adoption and integration of innovative technologies today. Fourth, shifting to long-term oriented, integrated regional planning strategies is needed to address the planning uncertainties that impede investment decisions. And finally, greater transparency and information sharing among industry is needed to address the technical maturity concerns and speed up deployment timelines. Solutions providers can play a key role here in supporting education and standard setting, advancing technology performance, and sharing performance risk with utility partners. The cross-cutting theme we have found is that accelerating deployment of innovative grid solutions requires shifting from legacy reactive grid management approaches to proactive, future-oriented strategies that serve the long-term interests of ratepayers. All right, now we have covered a lot of ground today. So in summary, there are really just 2 takeaways that I want you to remember. 1, we have an enormous opportunity to unlock significant capacity and modernize our existing grid by accelerating the deployment of commercially available, innovative grid technologies and applications. And 2, federal funding, like the GRIP program, along with LPO, OSED, and other programs, is available to support deployment of these types of solutions, including for high impact technologies like dynamic line rating, advanced conductors, HVDC systems, and ADMS and its advanced applications. At the DOE, we look forward to continue partnering with industry and the broader ecosystem to expand and modernize our grid. So with that wraps us up for today. Thank you so much for taking the time to join us. And we really would welcome your feedback on what we've covered today. Please send us an email at liftoff@hq.doe.gov, and your input will help us to refine our preliminary views and inform our full liftoff report, which is set to be released in early 2024. With that, I'll close this out for today. Thank you so much all. Have a great afternoon.